Fellow members, ladies and gentlemen, good evening. It is my pleasure to welcome you to the public lecture on HKIE Outstanding Paper Award for Young Engineers and Researchers 2025. We are delighted to have all of you here today, both at the Hong Kong IE headquarters and online. Your presence this evening not only recognizes the remarkable achievement of our young engineers and researchers, but also demonstrate your support for the continuous advancement of our profession. The HKIE Outstanding Paper Award has been an annual event since its launch in 2006. This award aims to encourage young engineers and researchers to innovate, publish their findings, and promote the engineering profession in the next generation. It is open to individuals aged 35 or below worldwide. This year, after a rigorous selection process, 3 outstanding papers have been honored with the award. The first authors of these papers are with us today to share their valuable insights. Before we begin, may I kindly invite you to switch off your mobile phone or set them in silent mode during the lecture. You are welcome to enjoy some light refreshments in the common area. Please feel free to help yourself. Now, may I introduce our awardee in the civil category, Mr. LEUNG Chiu, Winson, an electrical and mechanical engineer at the Drainage Services Department. His work focuses on the innovative application of robotics and artificial intelligence in stormwater and drainage services. Mr. Leung will present his award-winning paper titled YOSO, You Only Scan Once, a large small model co-adapter framework for AI-human collaborative Scan-to-BIM automation in wastewater infrastructure. Let's give a warm welcome to Mr. Leung.
So, good evening, everyone. I'm Winson Leung, an electrical and mechanical engineer from the Drainage Service Department. It is my honor today here to introduce our innovative framework, YOSO, which stands for You Only Scan Once. It is a large small model co-adapter framework for AI-human collaborative scan-to-BIM automation in wastewater infrastructure. And today's agenda will be divided into mainly 4 sessions. First, I will briefly introduce the background and the motivation of this research behind, and together with some insights from the literature review. Then I will move on to explain the methodology, how we developed the YOSO, and the key technologies involved. And then I will present the result and some findings from our field application, and finally with the conclusions. We wonder that why is DSD so interested in the BIM development? In fact, DSD managed extensive sewage network and drainage system, which is over 4,800 kilometers in Hong Kong. Also, we also manage more than 370 plants across Hong Kong. Managing such a vast and complex system requires tremendous resources and manpower. So improving the efficiency is one of the top priorities of our work. To enhance the efficiency, we have explored different approaches. For example, the MIC or the MIMEP to facilitate our replacement and upgraded works. Of course, we also more recently we also introduced digital twin technologies to enhance our operation and asset management efficiency. But these all technologies also share the same thing. They all rely on BIM models. Yet producing these precise BIM models is often time-consuming and heavily relied on the manual work. To create BIM models for existing facilities, the most common approach is the Scan-to-BIM workflow. This slide shows the general process. We begin by conducting an on-site 3D scanning to capture the physical environment and the point cloud data. And then the most time-consuming part is the next step. The engineer must manually segment the point cloud by identifying and grouping the points for the individual objects. Once segmentation is completed, the group points are connected together to form a mesh model, representing the shape and also the surface of each object. Finally, we enrich the model by adding attributes to transform into a real BIM model. To sum up, while the Scan-to-BIM workflow is effective, its main bottleneck is lying in the manual segmentation part. To address this bottleneck, many researchers have tried to develop some automated solutions. This image shows one example, a model that uses AI to detect and separate the objects directly from the point cloud data. But it works quite well in generic environments, but doesn't perform effectively in DSD facilities. First, we don't have enough data. DSD facilities, unlike a generic environment, the custom equipment doesn't appear into the open data set. As a result, we need to put significant effort to retrain the models such that we can use in our specific case. Second, the workflow is fragmented. Current research focuses on the AI algorithm and lack of the seamless end-to-end workflow, making it difficult to scale and automate the practice. Third, many of these models are not adaptive. For common objects like the chair or the tables, millions of open sources on the internet, which is available to find, which allows the ones to feed or training. But for our domain, with limited data sets, the model must be continually refined and updated with real domain-specific data and maintain accuracy and their performance. So these all challenges we are going to resolve. That's why it inspired us to develop the YOSO framework. Now let me introduce how the YOSO works. The core idea behind YOSO is quite simple, but quite useful. We integrate the edge intelligence, advanced AI processing, human expertise, and cloud calculation into a single connected pipelines, as shown in this slide. By doing so, we can make the entire Scan-to-BIM process faster, smarter, and far more adaptive. YOSO consists of three main stages. First, we have a small model, which operates on-site. Here, the device captures real-time spatial data and during the field operation. Next, the core adapter acts as the bridge between the field and the cloud, performing AI-driven segmentation and with the human-in-the-loop verification. Finally, the large model runs in cloud, refining the segmented data and generating BIM models automatically. Let's see how this helps us to overcome the challenge. Our core innovation lies in the design of the co-adapter module. It connects the small model and the large model into a cohesive end-to-end workflow. So it directly addresses the issue of the workflow fragmentation. At its core, we introduce a 2D pseudo segmentation. This process, instead of relying on large pre-labeled 3D dataset, we leverage the 2D image segmentation and positional data to perform 3D segmentation indirectly. This significantly reduces the computation and removes the dependence on massive 3D datasets. Third, the co-adapter modules also introduce a confidence-driven interface. When the AI detects the low confidence or ambiguous cases, it is immediately triggers the human in the loop verification. Engineers can review and correct the uncertain case, and then the verified data will be fed back to the model to retrain the model. Over time, as the model learns from these corrections, the need of the manual intervention steadily decrease, achieving continuous improvement through adaptive learning. In stage 1, the process begins almost exactly the same as the traditional Scan-to-BIM workflow. We capture the local point cloud data, but the slight difference is we use a small handheld devices that enable swift deployment and scanning. This device incorporates 3 main components. There is the LiDAR, IMU, and also the fisheye camera. They collect the position data, such as the depth and also the odometry, and the images simultaneously, and generate the color point cloud. After that, the co-adapter collects the color point cloud data and perform what we call pseudo-segmentation. Let's take the light tube as an example to illustrate this process. In the upper pipeline, the 3D point cloud of the light tubes is projected from 3D to 2D plane, preserving the key positional data such as the odometry and also the depth. At the same time, in the lower pipeline, the 2D colored images captured by the camera are sent into the YOSO model for object detection and segmentation. Once the objects are identified in the 2D environment, the resulting segmentation masks are mapped back to the 3D point cloud based on their corresponding positional data. Through this process, the 3D point clouds belonging to each light tube are accurately grouped together, effectively complete the segmentation task. By integrating the 2D image understanding with the 3D spatial data geometry, this approach avoids complexity of traditional direct 3D segmentation while still maintaining high accuracy and also the computational efficiency. During this process, when the AI detects the object with high confidence, such as these light tubes shown on the screen, the process will proceed automatically. However, for the low confidence case, say a flow meter, it will send this result to an engineer through an interactive interface. The engineer can quickly confirm or correct the classification, and the verified feedback will retrain the model. This mechanism ensures that YOSO maintains both efficiency and also the accuracy by allowing AI and human expertise work collaboratively. After the co-adapter completes the segmentation, the large model takes over the workflow. It refines the segmented point clouds, perform object clustering, noise filtering, and automatically generates the ready-to-use BIM models directly in the cloud. Now, how do we evaluate whether the YOSO truly works? Traditionally, the Scan-to-BIM accuracy is measured using the point level accuracy and also the intersection over union, we'll say IOU. However, these measures don't directly reflect the spatial fidelity. They tell us if the model is correctly segmented, but not how precise it is in the real world. Let's look at the point level accuracy first. These metrics measure how many points in the data set are classified correctly overall. More or less, it just consider the accuracy of whether 3D objects can be segmented. But if there are any missing part, we can still get a very high score in the point level accuracy, but it gives us a false sense of precision. For the IOU, which compares the overlap between the predicted model and also the ground truth by calculating the ratio between their intersection and union volumes. While this is a standard metrics in the computer vision, but it penalized both omissions and over segmentation equally without reflecting how those errors impact fabrication and installation. To overcome the limitations, we proposed two new metrics, which is called the intersection to human ratio, IMR, and also the Euclidean distance, the ED. First, the IMR measures the geometric completeness of each BIM components. Simply speaking, an IMR of 99% indicates the YOSO generated model almost completely overlaps with the human reference. This means nearly no geometry is missing and the risk of prefabrication errors is minimal. For the ED, it quantifies the positional fidelity. It means how precisely each component sits in the 3D space. It is calculated as a distance between the centroid of the components bounding blocks in the YOSO generated model and also in the manual model. A low ED means there's minimal deviation from the real-world coordinates. Based on these two metrics, we now present the YOSO results. The left-hand side image displays the BIM model of the light tubes generated by the YOSO framework, while the table on the right-hand side presents the corresponding analysis results based on the IMR and also the ED metrics. As shown, all 11 light tubes have been successfully segmented using the YOSO framework and clearly illustrated in the BIM model on the left. Apart from the light tubes, our YOSO also successfully segmented 5 more components, such as the gate valve, trap valve, air ducts, DI pipes, and also the flow meters. In this table, we demonstrated component-wise accuracy of the YOSO pipeline. As we compare the results with the manual modeling, so we assume the human output is perfect and as a reference line. So that means the IMR of the manual modeling is 100%, and also the ED is equal to 0 meter. In this study, we focus on the light tubes and the gate valve first because they have the largest sample size, and also they represent two critical extremes in the infrastructure, which is the standardized geometries and also the irregular geometries. As we can see, the light tubes achieve nearly perfect geometry completeness. We can see the mean value of the IMRs is almost 99.9%, but it has a little bit higher positional error over there. It may attribute it to the environmental noise, such as light diffusion on the reflective surface. On the contrary, for the gate valve, it do have a relatively lower IMR results, but the positional accuracy is relatively high. It may contribute to its nature. We also conduct the benchmark comparison between the YOSO and also the traditional manual Scan-to-BIM process for a 90-meter for a pumping station in this slide. We can see that the most substantial gain is the time efficiency. For the scanning time, our YOSO workflow can dramatically reduce the scanning time to around 10 minutes, and the whole processing time we have 80% of the reduction in the whole processing time. Finally, for the traditional manual workflow, it required the 100% manual input during the whole process. But for our YOSO workflow, we just need to, the human being just need to pay attention on those low confidence cases. Here we go to the conclusion. Although our YOSO framework was initially developed for the wastewater infrastructure, it designs highly scalable across the industry. It can be applied to construction sites, industrial plant, and also other asset-intensive environment, anywhere that large-scale spatial data needs to be transformed efficiently into intelligent digital model. Most importantly, YOSO delivers significant efficiency gain. It dramatically enhance the speed, accuracy, and also the scalability of the entire Scan-to-BIM workflow, and substantially reducing reliance on manual modeling and bringing us one step closer to the truly automatic data-driven digital transformation in infrastructure projects. Looking forward, our next steps focus on two main directions. First, the workflow enhancement. We aim to further refine the pipeline to improve the prediction accuracy and also the model robustness under the variety situation, including more complex geometries or the environmental constraints. Second, the AI-powered model completion. We plan to explore advanced AI techniques that can intelligently reconstruct the missing geometry when scanning data is incomplete. This moves us closer to achieving what we call the perfect beam reconstruction, even under less than ideal scanning condition. And finally, I would like to take this opportunity to say this project represents not just my own work, but a collective effort of a dedicated team. I would like to take this opportunity to express my thanks to all my teammates, Vasco Wong, Simon Lai, Kerry Jan, Paul Lam, Aaron Chin, Leo Wen, and our supervisor, TK Wong. Of course, also the judges for their invaluable comments throughout this journey. Thank you.
Thank you, Mr. Leung. It's a very interesting and successful project. We now open the floor to a 10-minute question and answer sections. For our online audience, please submit your questions via the Q&A feature on the screen. May I first invite questions from the audience present here? Yes.
Hi. I have two questions for our speaker. The first question is that why do you call it your system YOSO? And the second question is that what makes YOSO different from other AI-based scan-to-BIM solutions?
That's an interesting question. Thank you for asking. You may notice that the name of YOSO sounds very similar to YOLO. You only look once, which is a well-known deep learning model for the 2D object detection. Our inspiration actually came from this concept. In the 2D world, YOLO revolutionized the computer vision by detecting the objects in a single pass-through of the image. We want to achieve something similar for the 3D world. So a workflow that's where you can scan once, and then the system can quickly and accurately generate everything you need for the BIM production. So for the YOSO framework is here, it's designed for a single scan capture all the essential data for the BIM generation, and there's no need for rescanning or repeat manual processing. However, there's also a fundamental difference between the YOSO and YOLO. YOSO doesn't rely solely on a highly sophisticated AI model. Instead, what we have done is to unify the entire workflow from scanning to segmentation to human verification, and then finally the BIM generation into one integrated pipeline. In short, our YOSO, you only scan once, and the system will carry out the rest. I hope I can answer your questions. But for the second question, I forgot. Can you repeat the second question?
Second question is that what YOLO different from other AI-based scan-to-BIM solutions?
Yes, this question also actually touched on the core of our research. Most existing AI-based solution is focused on the scan-to-BIM, is a specific part of the workflow. Perhaps the scanning process, perhaps the AI segmentation of the point clouds. While these individual components may perform very well on their own, they often work in isolation, which makes the overall process fragmented and less efficient. YOSO is fundamentally different. Instead of developing another standalone AI module, we create a large small model called adaptive framework that unifies the entire workflow. One of the key strengths of this framework is that it is adaptive and it's adaptive. It doesn't rely on any single AI model or specific hardware. Whenever a new or improved algorithm, sensors, or model becomes available, our framework can integrate it and adopt it and keeping workflow future-proof. So YOSO is not just an AI model. It's a complete, intelligent, and collaborative ecosystem that brings everything together. Thank you.
Okay, thank you. We have another questions here.
Yeah, I have.
Yes, I have also some questions related to your project. First of all, I remember that there is also some 3D scanner in the market to create a BIM model automatically. So, and I also heard from your presentation that your stage 1 models rely on some sensors to have some the input data. So I'd like to know more about how if we change the sensors or some other tools to obtain the information, how it have the influence or impact to your AI model. And the second thing says, sorry that I'm not so familiar with the BIM technology, and I just heard about you have mentioned some for example the IMR or ED. So how can this kind of the things can help your model to have a difference with the traditional method to have a time reduction for the BIM making? And the last question is, I would like to also know more about the cost comparison between your YOSO and the traditional method, because I heard about the time reduction is very significantly, but I would like to also know apart from the time, also the cost, is this also have a big difference to this? Thank you.
Okay, thank you for your question. Let me try to answer it one by one. First, you asked about there's some maybe the intelligent edge devices. So you asked whether we can replace it directly. I think the answer is yes and no. If we go back to the slide, maybe the word is too little to see, and we can see on the left-hand side, the co-adapter can be adopted on the field and also the office/office operation. That means during the design of this framework, we also have left room for the future application that we may consider that the edge devices can be improved dramatically. Say we can have some on-site detection and segmentation immediately, and no need to bring this information go back to the office to carry out the next stage. So it is work. But the answer is no, is because as far as I know, under the current development, the edge devices is equitable to many generic environments, such as the office, or we can easily to identify the cats or dogs, which can easily find in the road. But for some specific domain specific environments, such as maybe the MTR, maybe the lift, maybe our wastewater facilities, the data, the 3D data set is still missing. So we're still waiting for the development of these devices. And for the second question, I think I would try to answer it concisely. I think our innovation is about, we are not going to develop every single step or every single module. We're not going to drill on a very sophisticated AI module. What we are doing is to integrate all market available devices and also the technology together to perform a unified workflow. But during this, we found that since this is a new framework, so we find that there's no metrics to evaluate our success. And that's why we abandoned these two existing metrics, such as the point level accuracy and also the intersection over union. And then we proposed these two metrics, the IMR and also the ED, in order to better evaluate our result. And these two metrics is actually applicable to the MRC and also the MRMEP project, because the IMR actually is talking about the completeness of the component, and also the ED is talking about the positional fidelity. So these two elements is really critical for the BIM model, such that we can have a clash-free installation in the future. And I think this is one of our innovation in our project. And the last one is about the cost. To be very honest, this is not the scope of our research, but I understand that the major cost of the current Scan-to-BIM workflow is the labor cost. So we can simply transfer the time saving into the cost saving, and that's the percentage of our cost saving. Thank you.
Okay, one.
Can you go back to the slide showing the accuracy measurements, please? Yeah. So according to your pilot work, the light tubes and gate valves, but gate valves not too bad. Light tubes very good. But these are pretty simple geometry components. If you go down the list, they drop to less than 50%. And there are many other drainage components of irregular or more complex geometries. What is your strategy in addressing the accuracy issues for these other less simple components? And what would be the targeted accuracy and why?
Thank you for a question. I think we can think this thing from this angle. First of all, we have to say that our framework is not to develop a very, very precise model for the object detection. Our major works is to test whether the framework, whether the pipeline is feasible or not. No matter the result is good or not, the major output is whether we can use this framework, this pipeline, to generate the BIM model. And you're talking about the difference in different results in different kinds of the components. Yes, but you can observe that for the sample size relatively large, the IMR and also the ED can achieve a better score. We can see that we can say in that way, because this is just a trial. We have a very limited data set. We believe that in the future, if we got more data set, more labeled data set, and we train in different sites and also in different scenario, the result will become better. But I need to emphasize that in our framework, we still have the human in the loop verification. And that means our framework could continuously improve through the correction of the human input. And also, when the day there's something new model, AI model that can identify or can segment the components in a very effective and accurate way, we can still adopt those models in the future. Thank you.
Okay, time is limited. We have one last questions, quick questions.
And just have a short question. What do you think about the potential for the future development of your framework and your model? Thank you.
Thank you for a question. I think it is a very interesting question, but I would like to quote a reference that we submit the paper on in 2025 in March, and our paper is on the research on the large small model, right? But at the same time, DeepSeek they also published another paper, which is also talking about the large small model co-adapter framework in 2025 April. So that means we think that at that moment, using the large small model co-adapter, which is just a trend to minimize the computational power at that time. But we can see the 3D calculation, the 3D model, and also the also the AI development in the 3D world is very fast. Today, we got lots of the advancement up to now, such as whether you know the professor called Lei Feifei. She is developing the so-called the real world model for which is called Marble. So I would say that let's see.
Okay. Thank you, Winson, for your insightful presentation. Now, let's move on to our next awardee. I'm pleased to introduce our awardee in electrical category, Ms. YIP Kim Man Coral. Ms. YIP is a senior design engineer for smart maintenance at MTR Corporation Limited, assisting in the development of various smart systems to enhance maintenance efficiency. She will present her award paper entitled Monitoring Tree Intrusion Along Railway Networks Using LiDAR Technology. Let's welcome Ms. YIP.
Okay, testing. So good evening, everyone. First of all, thanks for having me here, and thank you, Hong Kong IE and Professor Leung for the invitation. And I'm glad to represent the project team and the company to share one of our recent projects by using LiDAR technology to manage vegetation along our railway network, particularly the light rail network. So my name is Coral. I'm currently the senior design engineer from MTR. In the following time, I will introduce the project of Tree Intrusion Monitoring System, or we call it TRIMS. I'll focus more on how we bring this technology into real-world application. And I will cover the challenges of traditional methods in vegetation management in railway industry, and also how the system works, how is the configuration, and what is the benefits and social impact to enhance railway services and efficiency. So let's get started. As you can see in the photo and the videos, tree growing too close to our tracks can be a concern and may affect railway operations. MTR actually manages over 5,000 trees in the light rail network alone. Intrusions may cause power issues, say from branches hitting overhead lines, causing power outages, and events from service disruption or even incidents. And it's particularly more complex in light rail network because the light rail network come across the road traffic a lot. It's basically built inside the community together with road traffics. So MTR has been spending much effort in tree maintenance. Traditionally, one of the means we mainly rely on are by visual inspections through actual capturing right. And another means we employ external arborists for carrying out professional surveys on each trees along the network. The strategy has been quite traditional, classical, but it's quite tedious, reactive, and limited. It may be uneasy for one to master the whole network, and it's hard to get to know the condition of trees in a network-wise manner. So here's a view from the train cab during a routine inspection. In the traditional way, basically, our maintenance team conduct regular train rides to spot intrusion by eyeballs and based on their own experiences. It's particularly challenging in light rail because it has a lot of roofs and a lot of the environment is very complex. And also, trees are living things, they grow. And at the moment you inspect them, it's particularly sensitive on the environmental condition like rain, like wind. And trees are monitored for growth and health. We do tree pruning for high-risk cases. However, covering such a large area is very time-consuming, and practically the implementation can be affected by external factors like fog, rainstorms, and also distractions during inspections. And it highly depends on one's own experiences. So to sum up the key challenges on vegetation management, there is a high demand for human resources or regular inspection, and it means it ties up staff for frequent inspection and man hours. It's tough to accurately gauge distances from tree to track because it's basically purely rely on one's own judgment on site. And on-site practically, it requires repeated train rides if we wish to verify a particular location. That means if you have you want to verify a particular section of the track, you have to go back like 2 stops away, and then you take the train ride again, and then you ride all the way down again, and then repeat all the time. This can also result in over pruning or missing risk. So consolidator for planning tasks may take hours or days. So therefore, we need a smarter automatic way to manage trees and also to ensure safety without constant manual efforts. And that's why how we bring up this project, the Tree Intrusion Management System, which is the first LiDAR-based system in MTR mount on passenger train for daily in-service tree monitoring. So here is a simplified overview of the hardware configuration. Basically, the system is quite simple. It integrates LiDAR sensors that bounce pulses off objects to create 3D maps. And we use cameras, the high-definition cameras for recording footage, and it allows manual verification afterwards. And we have train-borne computer for edge processing. We have GPS and antenna mount on train roof to acquire location information. And we have particularly used 2 LiDARs of different facing directions, which aims to cover different parts of trees. One top facing is for tree crowns, and one forward facing LiDAR is for tree trunks. Data are transmitted via 5G between the train-borne computer and ground server computer. This setup covers the entire track without disruption in service, and our colleagues can access the man-machine interface, the MMI, via their workstation on a web link. So information can be shared among colleagues between teams easier and more coherent and faster. So this is the system architecture. Basically, the architecture splits into train-borne and ground components. On train, we have LiDAR that capture 3D point clouds. We have high-definition camera that records videos, the GPS track position. Data is processed via the mature SLAM, the simultaneous localization and mapping, and it's basically like how self-driving and those autonomous robots works and build maps. The data from LiDAR are time-stamped so that they can integrate with the GPS location. This allows the local data map into global coordination system. Unlike cameras alone, LiDAR works in rain or dark, so it has a lot better availability and without being affected by adverse weather. And for the backend server, it serves as the brain and intelligence for the post-processing, like the intrusion detection, and also the handle the alert flagging, etc. So here, introduce what we capture. We have the high definition 3D point clouds acquired from the LiDARs. It shows trees and all the landscapes in detail. We have video cameras mounted on train facing two angles. So here you may have a question why we need to have two LiDARs and two cameras. You may imagine actually one may do the job already. But actually, the light rail network is very special. It's unlike the heavy rail network. In light rail, the track is can be the curvature can be very small. I mean, the radius can be up to like 20 meter in radius. So the curves are very sharp. So if we only use one LiDAR and one camera, when the train negotiate very sharp curves, the angle may point to an unconcerned direction. And therefore, we carefully design the system to have dual LiDAR and dual camera mode in order to make sure we capture the whole network without blind spots. So next, I would like to talk about how we define our monitoring zones. And we touch a bit some very knowledge called the kinematic envelope. In the detection method, one of the very core part is the KE. We call it the kinematic envelope, which is the safe space. It's actually an imaginary safe space around the vehicle, accounting for like train sway, tilting, and track irregularities. Basically, it takes accounts of the vehicle dynamic movements. So it's a little bit bigger than the vehicles. And as you can see in the diagram, the red highlighted frame is the KE, or to simplify the KE. We have also defined the region of interest, which is the green frame, and also the orange frame, the size of warning zone. So we have 3 zones for monitoring, and this ensures we focus on threats without overwhelming data processing. We can exclude faraway objects and trees in the analysis. And the right diagram shows how it projects in a 3D manner. Basically, the trajectory is like a swept envelope along the railway network. So here I will introduce a bit the detection process and the workflow. All the point cloud data collected by the LiDAR are time-stamped, and then the point cloud map is generated into a 3D model through SLAM. And then we have the tree identification model. And after that, we would carry out the intrusion detection, followed by some evaluation. Basically, the detection processes is through the primary starts from the conversion between 3D map into 2D rasters. We identify trees from the 2D rasters in a bird's eye view and then projects back to 3D. And during the data training process, the trees are manually labeled and further carry out augmentation through a pipeline in order to carry out the data training to achieve a better precision. The system then carry out intrusion checks for trees only within the region of interest and intrude the defined frames. And eventually, the evaluation includes matrices like tree heights, volumes, and distance from tracks, which I will cover in the next slide. And all these results are presented in a meaningful manner through an MMI. So here, I will briefly talk about how we evaluate the risk of a tree and how we carry out the trend analysis. We use a very simple but powerful matrix. We define a height to distance ratio. It's basically the tree height divided by lateral distance of that particular tree from the track. And if the tree height is larger than the distance, physically it means when the tree falls down, it will lie on tracks touching the rails directly. So it implies this is of high risk, just like a tall tree leaning close. So this is the most primary and basic parameter we evaluate trees along the whole railway network. And apart from H/D, remember we have a top-facing LiDAR mount on train roof. We can capture parameters that can reflect the volume of the tree crowns. So we can evaluate the volume together with tree height and distance from track. And then we can basically use some simple mathematical equations. We can score each tree, and then we can scale for loss. We have also include growth prediction, use historical data, and it compares like past data, and then it allows some insights like monthly averages. So this is how the MMI, the man-machine interface looks. It basically displays live footages, suspected intrusion case log. The user can verify one by one. And then it includes some key dimensions like location, height and distance, and some visualization of the overall data through heat map and index map, which is very useful that the user, our frontline users, can use the map to have a feeling on how the conditions is like in the whole network. So basically, this project transformed very traditional vegetation management to a more centralized way and more scientifically. So, okay. So traditionally, fragmented data, now we have a centralized platform to oversee tree conditions in the network. We have used a high H/D ratio to quantify the trees, and we use some risk scores that specially designed for the network. We can have heat map and time series trends analysis. We can further group parameters using simple mathematics to become different indexes for some intuitive dashboards to prioritize risk zones and trees. And what's more, user can visualize the conditions as a network-wise manner to gain feeling on the overall condition for better planning. This is particularly valuable, especially for a network of over 5,000 trees. And this project has acquired short-term Hong Kong patent and received some various positive results in different local and international competitions and expos. And more importantly, we gain a very positive feedback from the frontline users. And this is the most valuable because we always think that to put some technology to bring to the front line is rather difficult. We are very happy to know this system can assist their daily maintenance work, assist their planning, and reduce some of the manual efforts in cab ride. So here comes the conclusion of the project. Basically, the key benefit of the project is it provides a holistic and automatic way to inspect trees and vegetation, and it reduces some human effort in train ride, and it also helps preserve the trees to reduce over trimming and aligning our corporate ESG goals. It can manage risk more effectively, and to my opinion, I think the project is quite scalable to other outdoor network and very nice. So this is the end of my presentation. Thank you very much.
Thank you, Ms. Yip. We now move on to the questions and answer sections. I would like to invite questions from the floor. For those participating online, please submit your questions through the Q&A features available on your screen. Okay, we have questions there.
Yeah, thank you.
Hi, it is excellent sharing. So, I'm interested in more in the approach of how to predict the growth of 5,000 of trees. Is it by the category or other way?
Oh, thank you for your question. Basically, for over 5,000 trees, the model actually evaluate trees in groups. So the growth actually evaluates collaborative score on a tree groups. To give you a feeling, a tree groups is around like 40-meter diameter. We call it a tree groups. And if you remember, I have shared that we have two LiDARs. We have some LiDAR that capture a point cloud that can represent the volumetric space of tree crowns. And we have LiDARs that can capture the height. So we can use some simple equation to mix up these simple dimensions that reflect the size of a particular tree or a tree groups. And then we compare the historical data of such dimensions of that tree groups in the same location. And then we can predict the growth rate of that tree groups. Yes. So it's pretty much simple. It's just like a little bit tedious because the number of trees is as so many, that over 5,000. The principle behind is rather simple.
Yeah, thank you very much. And I got another question that I'm very curious about the data collection is that can LiDAR work at under like foggy, extremely foggy condition, because it might happen in Hong Kong. And if there is a foggy condition in Hong Kong, if it's work, then will the data, if the data is not precise, will it like, make the system messy?
Actually, we work like this. For vegetation management, we compare how the system works with the traditional way. The system is valuable as long as it's better than the manual like eyeball inspection. In vegetation management, we do not require a very high precision dimension measurement like the BIM model, because traditionally we just rely on like manual on-site judgment. As long as we have LiDAR, it's already better than the traditional way by a lot. To answer your question, in foggy weather, it did affect a little bit, but we can control because we only mount one system on one particular LRV. We can control how we use the LRV to do the automatic inspection. We can arrange whether we still carry out or we shut down the system when we think the adverse weather may affect the data a lot. And when we have sufficient data, we can also trim down or we can screen out those outliers. So it did affect a little bit, but it in general case to compare with traditional way, it doesn't matter that much. Yeah.
We have a couple questions from the online audience. Let's answer some of these questions. The first question is, using camera to conduct object recognition is often limited by its resolution. How did you overcome this challenge?
I see. I believe they may referring to like high definition camera for object detection. So this project basically is a mixed mode. It uses LiDAR for capturing point cloud and also the high definition camera. The high definition camera actually do not contribute much in object detection. It basically connects the frontline users because we need the footage to allow the frontline users to do manual verification, to locate the location more easily. So actually the camera in this system provide different function. It doesn't contribute much to it do not actually work as object detection. The object detection purely rely on LiDAR, which do better than high definition camera, I believe. Yeah.
Okay, thank you. And then we have another question from the online audience. The question is, as vision-based object detection is very advanced and cheap now, does it make LiDAR system adopted obsolete? Now some cars can drive themselves using vision-only system without needing LiDAR. Shall I repeat the questions?
Oh, yes. Can
Okay.
I-
Well, basically the question is there are more advanced object detection technologies. So how do you compare the advanced technology with LiDAR?
Actually, in a very system, whatever we need to install something on train, we need to consider a lot of things like whether the technology is mature, whether the technology itself can meet some very stringent, very standards. There are a lot of international standards we need to meet in order to bring something on train. So for those more cutting edge, more advanced object detection, we have to compare whether it's mature enough and is applied in some very environment. So basically in the railway industry, I believe some more mature and some proven products are generally be selected for any trials. So this is my opinion on the comparison. Yeah.
Okay, thank you. Any more questions? Yes.
Yes, please.
Thanks. It's a great presentation. Thank you.
Thank you.
Thanks a lot. I have two questions. First of all, I wonder what's the consistency of the data? So to me, it seems like the LiDAR to be a time spatial data. So you can pass through a tree for several times. So I wonder, is the data for a single tree, is it consistent mostly? Or for example, we can get very different readings for single trees. The second question is, do you have a rough number of how much money or how much manpower
That's pretty sensitive.
that is saved through this
Yes.
project? Yes.
Sure, thank you. Thank you for your question. That's an interesting. The two questions are interesting. Let me address your first question first. Actually, we combine the LiDAR data. You're right, it's time-stamped. And actually, we also integrated GPS data, and I didn't mention that much. We also integrate some train-borne location data that particularly is very related. We directly get the location data from train, and actually, train has a different way to locate itself. It basically combines the station. We have something like station codes, and we have the sensors from the SON. We have a wheel set, we have SO, and it spins when the train moves. We have very precise location data. And we combine the location data on train we get, and we combine GPS, and then we integrate them with the LiDAR. So actually, in this project, we achieve pretty good repeatability on the situation that you have mentioned. And for the second question, actually, this is a pilot project. We try to transform the traditional vegetation management way to a more modern and more scientific way. It's hard to say how much money is saved, how much man-hour is saved, but the whole platform brings something that is not possible in the past. In the past, we do not have a very good dashboard to show the whole network. We do not have heat map. So basically the maintenance managers have to, based on their own experience, the very discrete data they get from the technicians, and then to have a general feeling on the network condition. But here, after we get this system, we can have a more scientific way. We have a really pretty dashboard to show the heat map, to show the index map, which can offer a very good alternative for planning. So with this system, we can reduce, I believe we can reduce the over pruning, but it's hard to say how much time of pruning of trees is saved for each year. We also need more time for observation. We have been using this for around 1 year, and we need to observe more years, and more particularly the typhoon seasons, in order to maybe adjust some of the parameters, some of the assumptions, like whether H over D ratio is good. Maybe we need to adding some weighing coefficient to different parameters. All these things we need to observe, and then we need to like feedback to the system to make it better. Yeah.
Okay.
Thank you.
Thank you. Let's thank Ms. Yip again.
Thank you. Thank you.
We now proceed to the final presentation. Now let me introduce our awardee in the mechanical category, Mr. Zheng Yong Jasper. Mr. Zheng is a senior consultant at the Hong Kong Productivity Council on new industrialization and is an Industry 4.0 implementation consultant accredited by the Fraunhofer Institute for Production Technology. He will present his award paper, Gamification and Digital Twin, a synergistic approach to enhancing manufacturing processes in Industry 4.0. Let's welcome Mr. Zheng.
Thanks so much for the HKIE invitation, and also Professor Michael. So I'm first time here, nice places. This is Jasper. So we can start it right now. Okay, today's topic is mainly about gamification and digital twin. Okay, by combining them approach to enhancing the manufacturing process in Industry 4.0. Okay, but at the beginning, I would like to talk about I 4.0, since many people are talking about Industry 4.0, but I'm pretty sure that not many of people have ever seen the actual definition of I 4.0. Okay, basically here is the background information initiated in 2011 and formally defined these terms. And a report and deployment strategy was submitted in April 2013. Okay, led by the German Academy of Science and Engineering architect. Okay, there are main key stakeholders and also some R&D institute. Okay, you can see the key stakeholders are included the private sectors, famous private sectors like the Trump doing the laser technology, BMW for automotive, HP for 3D printing, Festo for pneumatic, and ABB and Siemens are mainly for the industrial automation. And also the major R&D include the Fraunhofer, especially including the Fraunhofer. And okay, so, and here is the actual definition of Industry 4.0. And you can see that Industry 4 mainly including the new level of organization and control, included in the whole value chain life cycle of products, and creating the dynamics of organizing real-time optimized value-added connection, okay, within our cross company. Okay, here is the deeper interpretation. I will not go through one by one, but on the right-hand side, you can see from the definition, you can divide the Industry 4.0 into four different levels: 1I, 2I, 3I, and 4I. You can see I especially highlighted the 2I and 3I since it's mainly related to the digital twin, digital strategy shadow. Okay, in level 1I, mainly talking about the capturing the real-time data by sensors. Okay, level 2I is mainly talking about the using the data, creating the digital shadow, and for the 3I, it's talking about a cyber physical system. Okay, and about the digital twin, and also the last one, the ultimate level is mainly talking about data autonomous. Okay. In a nutshell, okay, what is Industry 4.0? It's not purely about automation. We are not talking about the robotic arm. We are not talking about the non-standard automation system. We are talking about using the data to generate outcomes, the value added. Okay, since a simple say, automation is releasing your muscle power. Okay, but for I 4.0 is releasing your brain power by using the data autonomous, generating the other value. Okay, and okay, here is the background about this paper behind. Here is today's reality. This data is mainly from the GBA. I'm not sure whether you guys have the concrete concept about the Greater Bay Area. Okay, actually include 11 cities: Hong Kong, Macau, Guangzhou, Zhongshan, etc. Okay, the total area of these 11 cities is only 0.6% of the total China's land area, but contributing the 11% of the total GDP of China's total GDP. So that means it's really a high potential area we need to focus on. Okay, here are some problems in this area. Okay, the first problem is about the skill gaps. Okay, you can see here, 65% of the advanced manufacturing firms in the GBA rely on external experts for the digital system and automation system. Okay, and in Shenzhen, some data in Shenzhen, Shenzhen's vocational institute graduate approximate 20,000 students annually in manufacturing related field, but yet local factory require 150,000. Okay, skilled technician. And another problem is about engagement. Okay, people doesn't like the manufacturing fields. Okay, young people, especially for young people, only 28% of the frontline workers in Guangdong province reported high engagement. Okay, so that's so we think about what is the future manufacturing is look like. Okay, imagine that in a factory, people operator wearing the VR, AR headset and collaborating with the AI artists. Okay, what we think is that maybe gamification with the digital twin can help to solve this problem or provide to generate a resilient, dynamic, and human-centric environment to help the workers and also the accelerate the innovation. And here is the key concept of gamification. Okay, the definition is really simple. Use the game mechanics to drive the real outcomes. Okay, the outcome we are talking about the reducing the resources, use less material, and also generating the more profit. This is mainly for the businessman, okay? And also the gamification tap into the basic human motivation, competition, achievement, and collaboration, okay? The core mechanisms including the points, real-time feedback, storytelling method, and progression system, okay? By using this, okay, we can motivate the people intrinsically, and also we can by forming a culture, we can also providing the rewards extrinsically, okay? And here is the key concept of digital twin, since we work closely with the Fraunhofer, and also I'm the accredited consultant from the German Fraunhofer. And you can see what are the exact definition of digital twin or key concept. You can see here different buzzwords: digital asset model, digital shadow, and digital twin. And the first component is about the digital model. Okay, it's mainly generated by the CAD software. Okay, it's mainly used for showing the behavior of different physical counterpart of a model. Okay, mainly showing the geometric data. Okay, this is the first part. And the second part is about the digital shadow. Digital shadow is mainly showing the real-time data. Okay, by using the technology sensor, you can capture the data of that device or that machine, mainly showing the real-time status data, operational data, or process data, like the picture here over there, the full pressure, temperature, or vibration or power. Okay, by combining these two, digital asset model and also digital shadow, this is the final digital twin. Okay, this is the comprehensive real-time data model of a specific asset, and also including the full life cycle data. Okay, including the historical data, and also this is mainly used for doing the prediction, mainly doing for the monitoring and also diagnostic. Okay, we can use this digital twin mainly for the data model, machine learning model. Okay, to supporting the whole maturity level of a different level of the AI 4.0 maturity level. Okay, so our idea is combining the gamification and digital twin. Okay, gamification acts the engagement to digital twin, and digital twin provides a scalable, immersive platform and enable technology for gamified workflow. Okay, in other words, is that I think that gamification is turning the data into the engaging story. Okay, to let people more engagement, increase the engagement of the people. Okay, here I will briefly talk about the technology enabler. I'm pretty sure that you guys know this well. Okay, for sure. Since we need to connect with the virtual world and also the physical world, so the IoT edge computing as part of really essential technology for that, and also the AI-driven analytics, mainly for correlating the operator performance with the historical data sets, and also generating the personalized gamification mechanics and also the predictive analytics. Okay, and finally is the XR, including the VR, AR, and also the MR. Okay, just providing immersive environment between the physical and virtual. Okay, and okay, here is our implementation framework. You can see here, including the 3 layers, and okay, the first critical layer is the digital twin layer. Okay, including the geometric data and also the process data, operational data, and then we form the digital twin layer by using the IoT analysis simulation. And also you can see the blue color one is a gamification layer. basically data from the digital twin fit into the gamification mechanic and the gamification layer. By using the narrative points or some real-time dashboard, we can drive the user action, okay, via the HMM. In the HMM layer, the human-machine interface layer, by using the advanced human-machine interface like treadmill, VR headset, or some haptic shoes, okay, we can interact with the physical world and also the virtual world, okay. Okay, here the physical setup, okay, basically you can see different layer embedded into different IT infrastructure. Okay, the human machine layer, including the treadmill, VR, HMD, and also by using the separating the different show in the different sensor, and then we'll put the different engine into the digital layer and also gamification layer, and then we by connecting the physical cell by using the network, you can see inform the physical cell. And here is one of the example with the develop, and also we applied it in the 3C accessory factory in mainland China. Okay, you can see basic problem. I don't know whether you guys have some knowledge about the industrial robotic programming. Okay, it's mainly like if you are a computer science or a coding guy, you must have some experience on the C coding. Okay, basically the industrial robot teaching programming is really like the C programming. So if we would like to make the robotic arm program more efficiency, we try to implement the virtual twin to help solve this issue. Okay, and also a lot of the small and medium-sized manufacturer do not have a skillful programmer for the robotic arm. So we try to use this idea. You can see here some video showings. The physical side is in Foshan. Okay, physical is in Foshan, and the virtual twin is in Hong Kong PC in the Kowloon Tong. Okay, we try to using the VR headset and also the treadmill, and then we can simply program the robotic arm by drag and drop. Okay, so this have a different benefits, enhance safety, and and reduce the downtime. Seems we can change over faster and also increase the collaboration efficiency, and also have another advantage about the lead to bulk, since we just need to one skillful robotic programmer in Hong Kong, and then we can control many physical cells in different places. Like maybe some physical cell is Foshan, some physical cell is in Dongguan, some physical cell maybe in the Germany. Okay, we can easily by using just one professional people to do this. And also, as I mentioned previously, we have implement this setup into a 3C accessory OEM factory. Okay, about doing the communication device accessory. You can see the figure is really encouraging. Okay, 88% of reduction in the light changeover cycle time. Okay, 9 days to 1 day. Okay, that means they can have more capacity for the production. And also you can see the productivity is increased 4 times. Okay, 20,000 pieces per day to 80,000 pieces per day. Okay, this is really encouraging. Okay, and another example is also use a similar implementation framework, also developed by the HKPC. Okay, seems this day automation is really mature, but some working process is still labor intensive, especially like the garment industry. Okay, manual people. So we still need to have people's data to enhance our process, right? So we try to use the sensors and also the virtual twin by using the different sensors, like the 2D sensor, like the camera, and also like the proximity sensor, like we may also use the 3D sensor to capture the motion of the purple. Okay, by capturing the motion of the purple, we can have the data of the purple. Okay, the working data of the purple, and also by using the purple, we can fit into the twin. Okay, we can fit into twin, and then do the simulation with the twin. Okay, and then you can see my colleague using the treadmill and the VR headset and doing the working process simulation in the virtual environment. Okay, we can use the data. Okay, and find the bottleneck of different working process. Okay, and then we can provide a suggestion for how to enhance this process. Okay, this is this project for, and it's really good that quite encouraging that apart from helping the enterprise, we also get a lot of the local and the global recognition. Okay, from the USA, from also from the Switzerland, and for sure. Okay, when we are implementing this technology, there are some challenges. Okay, technical. McKinsey, so famous consultant company, shows that 70% of the industrial 4.0 pilot failed due to the incompatible legacy infrastructure, and also the economy, since build a 3D model is really quite expensive. Okay, especially for the digital twin, not the purely the CAD model, okay? And also for the human, okay? I remember that last year, April, I go to Germany and I present a similar topic, and then a elderly ladies and come to me, hey, Jasper, is it really can help us to get into the environment again? Okay, since she mentioned that it's really difficult for elderly people to get to use the computer, to use the VR headset. Okay, I agree that. Okay, this is really a challenging for people. There should be a learning curve for them to adapt to this new technology. But I'm really happy that that lady also told me that it's about okay, but seems that we would like to get into the environment again. We would like to express our value. Okay, we are really willing to try this new technology. Okay, so that's why what my point is that right now I'm not sure whether the AI can replace the people. Okay, but I'm pretty sure that people is really the core of the future. So providing the value, and also I really believe that the future, some process still need to rely on people. Okay, and if the last generation people still can embracing the changes, okay, I'm firmly believe that young generation or my son or my daughter can have a great future under this new technology era. Okay, and also the last part is last but not least is the future trends. Apart from the AI, we firmly believe that one of the research direction is our high-tech shoes. Since when you have the Meta Quest or the Apple Vision Pro, it's really quite difficult to use. Okay, and we don't have the haptic shoes for the response of our body. Okay, I think the haptic shoes is one of the interesting out in the way, the wearable device and the different immersive improvement outcomes, and will come up. Okay, and okay, lastly, here's a problem again, but these are also the opportunities. Okay, so thank you so much, and see whether we can have more discussion during the Q&A session. Yep.
Okay, thank you, Jasper. Okay, let's move on to the question and answer sections. For the online audience, please submit your questions using the Q&A features. And any questions for the audience here? Any questions? Yes, please.
Thanks. So great presentations. So I'm wondering, so you said you kind of use the VR set to help the robotic arms in different physical location of the factories. And I just wonder, when the factory condition change, is the digital twin model constantly evolving, reflecting the change in the factory condition? For example, we can have some obstruction, and I wonder, is it very costly to update this digital twin model, or is it very easy to update to consider all the condition and then update the robotic arm? What is the process like? Yeah, thanks.
Okay, this is really a quite interesting question. So maybe I answer by using this slide. Okay, in my experience, when there is a new machine, new system in the physical cell, okay, really, as I mentioned, digital twin is including the digital model and also digital shadow. Okay, I agree that it's really quite time consuming to build a new digital twin. But But the future is that I know that there are many research by using AI to generating the new digital twin. I think this is one of the interesting direction you can look into. But at this stage, since we are talking about digital twin, especially for the machinery, it includes the data, include the mechatronic system. It's really difficult to simulate the mechatronic system of the machine, not purely the geometric data. So right now, I agree that it's time consuming. Yeah.
Jasper, I have a question. It's very interesting work.
Yeah.
Okay. Well, you have presented the performance of the digital twin very effective in increasing productivity.
Yeah.
I have a question. Can you apply this technology in other applications? For example, fault detection of the machineries, or can it support maintenance and repair work of the system?
Yeah. Thanks, Professor's question. Sure. Yeah. Seems the digital twin is included different whole life cycle of that machine, whole life cycle data of that machine, including the historical data. Okay, basically, by using these digital twin, okay, for sure the data we can try to do the data correlation and also the analysis for the maintenance plan, for sure. But for also by using the virtual environment, okay, since people can do the simulation first, so people can use the machine properly, and this also can help the machine's health status. Yeah.
Okay. Okay, thank you. Any questions? Okay, if not, let's thank Jasper again.
Thank you. Thank you.
Having heard all the presentations, I would like to extend my heartfelt gratitude to all our awardees for dedication and valuable insights have greatly enriched our event and inspired us all. The award papers presented today have already been published in our award issue of the HKIE Transactions, Volume 33, Issue number 4. I encourage you to visit our HKIE Transaction website for full access to these papers. Looking ahead, HKIE will organize the HKIE International Outstanding Paper Award for Young Engineers and Researchers in 2026, strongly encouraging submissions from young engineers and researchers around the world. The award continues to serve as a platform for professional recognition and international knowledge exchange. HKIE encourages aspiring young engineers and researchers to participate in the event, showcase their innovations, and contribute to the advancement of the engineering profession and society. Let's continue to foster innovation and excellence in engineering. I hope to see you all again next year. Thank you.